Welcome to the Problemers channel, season 3, episode 9, the episode which I titled Finite Sums Evaluation via Double Counting, because in this episode we will do just that. We will discover a way to evaluate certain finite sums, borrowing the idea of double counting from combinatorial analysis. But before we deep dive into the underlying mathematics, as a traditional and friendly reminder, if you're joining our channel mid-season, then first of all, thank you very much for your vote of confidence. Thank you for subscribing to our channel and welcome to our channel. And second of all, perhaps the most efficient way for you to gain the most academic benefit for yourself by working with the material that we present on this channel is for you to go to the homepage of our channel, and at the top of that page in the channel's trailer section, find the episode titled The Problemers Channel How To. We suggest that you watch that episode in its entirety, follow all the instructions that were given that episode, because in that episode we explain and motivate everything that we do on this channel. And if you have any questions, then by all means do ask. Find an episode that is of interest to you, use the comment section in that episode, and I will do my best to answer all of your questions. The challenge of the mathematical problem S3E9 was to find a way to evaluate certain finite sums, borrowing a popular in combinatorial analysis approach to generating proofs of combinatorial identities, and then apply that idea to the evaluation of the following infinite sum. The common term of that sum is a ratio of the index, summation index n, that sits in the numerator, and in the denominator of that sum we have the Euler's constant e raised to the summation index n. If you were not able to solve this problem correctly and on your own, we suggest that you practice mathematics correctly, and on that channel we suggest that you find the episode titled Season 1, Episode 2, How to Practice Mathematics Correctly. Watch that episode in its entirety and follow all the instructions that were given that episode. I hope that the idea that you were expected to generate on your own while solving this problem was literally lying on the surface, because one of the first things we'll learn about generating proofs of combinatorial identities is precisely that, double counting, an idea or an approach that comes in two fairly distinct flavors, a more formal flavor and a less formal flavor. With a more formal flavor of double counting approach to generating proofs of combinatorial identities, we interpret the left-hand side of a given combinatorial identity, such as this sample 1, as the size of a certain set. Let's call that set L for left-hand side. And we interpret the right-hand side of the given combinatorial identity as the size of yet another set. Let us, for demonstration purposes, call that set R. And for a technical proof that the given combinatorial identity does hold and is true, we try to construct or identify or find a bijection between the two sets, L and R. For example, one way to prove the combinatorial identity shown over here using this more formal flavor of double counting approach is to saturate the abstract mathematical objects that are baked into that identity using the powers of your imagination. Here is, for example, my take. Let us say that n is the specific number of flowers. And then what do we call an arrangement of some number of flowers in which the order of these flowers and the repetition is not allowed and the order does not make any difference? Well, such an arrangement of flowers in which the order of the flowers does not matter and the repetition is not allowed is called a bouquet. And a typical popular definition of a binomial coefficient is precisely that. In how many ways can a bouquet that contains, let's say, k flowers be arranged? Precisely in the n choose k ways. Consequently, in this case, we interpret the left-hand side of the given combinatorial identity as the size of the set of bouquets, each of which has an even number of flowers. For example, let's say n, for demonstration purposes, will be equal to 6. Then we are looking for bouquets of 6, made up from 6 distinct flowers that have exactly 0, 2, 4, and evidently 6 flowers in them. Incidentally, if we crunch the numbers, then it will be evident that that number in this case comes out to 32. Again, we take n to be equal to 6. Likewise, we interpret the right-hand side of the given identity as the set of bouquets made up of n, the same number n, of the same distinct flowers, but each bouquet in that set has how many? Has an odd number of flowers in it. So in this case, for our sample number of 6, just to have some concrete material to work with, we're looking for bouquets that are made up of 1, 3, and 5 flowers, for example. And again, based on one popular definition of a binomial coefficient, which is what? Which is a number of ways in which k distinct items can be selected or chosen from the set of n distinct items. Now we have two sets. Let's call the set that corresponds to all the evenly sized bouquets as E, for example, E, and the set that contains all the bouquets that have an odd number of flowers in them, uppercase O. The question is now, how do we establish a bijection? How do we establish a bijection between the set E and the set O? Again, at this point, it should be evident that the number of bouquets that have, for example, 2 flowers, 2 distinct flowers in them, is equal to the number of ways in which 2 flowers can be selected from the set of 6 flowers. And that number is given by n choose 2k. In this case, k is equal to 1, and so on. Consequently, the total number of bouquets, each of which has an even number of flowers, is given by the left-hand side of this identity, and this is precisely what we do in the more formal flavor of double counting. We interpret that number as the total size of the set of the bouquets, each of which has an even number of flowers. And likewise, by the same reasoning, we will say that, for example, the number of bouquets constructed from 3 distinct flowers chosen from the set of 6 is equal to what? 6 choose 3, or n choose 2k plus 1, where k in this case is equal to 1. Consequently, the entire set or the size of that set will be given by summing all such binomial coefficients and varying k accordingly. Here we do not specify the exact upper boundary because we know that once the bottom of the binomial coefficient becomes larger than the top, then this coefficient becomes 0, vanishes. And again, coming back to the idea of more formal flavor of double counting for generating proofs, how do we establish a bijection between the set E and the set O? Well, that is quite straightforward to do. Let's say we have a flower, one of the flowers that we have at our disposal is called a tulip. Is called a tulip. So now we go back to our set E. We know it has, let's say, in this particular case of n equal to 6, 32 elements in it. It has 32 elements in it. Altogether, we pick any element, it doesn't really matter. We pick any bouquet that has an even number of flowers in it, and we ask the following question. Is the flower tulip in that bouquet? If this flower tulip is in this bouquet, then we simply remove it. And if this flower called tulip is not in this evenly sized bouquet, then we add the tulip to that bouquet. And in this case, the fact that 1 is added to or subtracted from an even, let's say 2m plus or minus 1 even number of flowers, makes the total number of flowers in this case what? Odd. And that automatically means that that bouquet will correspond to some element in the set of all the bouquets, each of which is made up from an odd number of flowers. And conversely, that process is totally reversible. If we pick any specific bouquet that has an odd number of flowers in it, and we ask the following question directed toward that bouquet, is the flower named tulip in this bouquet? If it is in that bouquet, then we remove it from this bouquet, and if it is not, then we add the tulip to that bouquet. And in this case, what happens? In this case, what we have is an originally odd number of flowers, let's say 2n plus 1, and we add or subtract 1 from it. And in the first case, we get the number which is what? 2 times n plus 1, which is even, or we get 2m plus 1 minus 1, or we get just 2m. Either way, the number is even, and that automatically means that this bouquet corresponds to a bouquet from the set E, which has precisely an even number of flowers in it, and that concludes the establishment of a bijection between the set of even sized flowers and odd sized flowers. And thus, because we managed to establish that bijection, the identity that we see over here on the board, a sample identity, does hold true and is correct. With a less formal flavor of double counting approach to generating proof of combinatorial identities, we interpret a given combinatorial identity as an equality between the results of two different ways of counting the number of possible arrangements of one and the same set of one and the same objects in a prescribed fashion. One such way represents or convincingly explains, let us say, the left-hand side of such an identity, and another such way of counting represents or explains convincingly the right-hand side of the given identity. We then argue that precisely because the number of possible arrangements of one and the same set of one and the same objects remains one and the same regardless of how that number is counted, we have the right to put the equal sign between the two sides in a given identity, and thus that fact establishes the validity of that combinatorial identity. For a demonstration of how this less formal double counting approach works in combinatorial analysis, let us prove the following combinatorial identity. The sum of all the legal binomial coefficients is equal to 2 raised to the power of n. Again, the way in which you saturate a given set of abstract mathematical objects with concrete material depends on your mathematical imagination, on your tastes, on your creativity, on your level of experience and maturity, and so on. So let us say, for demonstration purposes, n represents the number of distinct toys, and represents the number of distinct toys. And what do we call an arrangement of some number of distinct toys, in which the order of these toys does not really matter and in which the repetition of toys is not allowed? Let us say we'll call this arrangement a gift for a kid, for example. Then, in order to prove this identity in a less formal flavor of double counting, we want to invent a story, a plausible story that will represent or explain, let us say, the left-hand side of this identity as follows. The number of gifts that can be constructed from n distinct toys that contain precisely zero toys is equal to what? Is equal to the number of ways in which 0 distinct toys can be chosen from the set of n in an order-insensitive fashion when repetitions are not allowed, and that number is given by n choose 0. Wonderful. Now, when we iterate k from 0 to 1, what do we get? The number of gifts that can be formed from one toy is equal to the number of ways in which one toy can be chosen from the set of n. That number is given by the binomial coefficient n choose 1, and there we have it. Iterate k one more time. The number of gifts that can be formed from n distinct toys in such a way that that gift contains 2 distinct toys is equal to the number of ways in which 2 distinct toys can be chosen from the set of n such toys in an order-insensitive fashion. Repetitions are not allowed. That number is given by n choose 2. Wonderful. We have it on the books, and so on. In general, the number of k-sized gifts that can be constructed from n distinct toys with repetitions not allowed, and the order of the toys where the order of the toys is irrelevant is equal to the number of ways in which k such toys can be chosen from the set of n. That number is given by the binomial coefficient n choose k. And if we sum all these numbers over k over the legal values, once you get used to this, you will simply say greater than 0. You can even put positive infinity over here, because the moment k steps over n, the binomial coefficient vanishes and the game is over. But that story represents the left-hand side of our identity. That is one way of counting the number of possible, the total number of gifts that can be constructed from n distinct toys, k toys per gift. Now we need to invent a different way of counting the same number of arrangements, the same number of gifts. How can we do that? Well, again, here A story that you invent depends on your imagination, creativity, level of experience, taste, maturity, and so on. So here's one way. When we construct a K-sized gift from the given toys, we go through all the toys one by one, and on the toy by toy basis, we ask the following question or make the following decision. Does the given toy belong in the gift basket? Yes or no? And we notice that the answer to that question has only two possibilities. Yes, the current toy does belong or goes into a gift basket, or no, the current toy does not go into a gift basket and will not participate in the formation of the gift. And we also notice that the specific answer to that question does not affect the number of possible choices for the next toy, the number of outcomes, or the number of answers to the question that we will pose for the next toy. That means that multiplication counting principle applies. The choices, the number of choices that are available for each toy are independent. And that means that, for example, for the toy number one, we will have two choices. This toy is either in the gift or not. And for each such choice, the next toy will also have two choices. It is either in the gift basket or it is not. And so on. Here we will have precisely n twos, and all this chain of twos collapses into one beautiful expression, 2 raised to the power of n, and voila. We argue that regardless of how we count the number of possible gifts that can be constructed from n toys in such a way that the order of toys in a particular gift does not matter and repetitions is not allowed, is one and the same. Consequently, the identity shown over here is valid, does hold, and is true. And that is how the less formal double counting approach to generating proofs to combinatorial identities work. And now that we have more or less a reasonable idea of how double counting approach works in combinatorial analysis, let us see if we can parallel translate that idea from combinatorial analysis into the context of finite sums. On the one hand, it does take some time to master the art of using the double counting approach to generating proofs and combinatorial identities and bring it up to snuff. But on the other hand, and that was the real challenge of the mathematical problem S3M6, is to generate an idea that sits on a level that is higher. And unfortunately, I would say many students do not generate this idea. And that idea is the following. What will happen if we try to parallel translate the double counting approach to generating combinatorial proofs in combinatorial analysis from combinatorial analysis to, let's say, algebra or real or complex analysis, and try to use that approach to evaluate certain finite sums? You see, the way things work is that we usually, or many students usually, think that the vaguely defined distinct layers of mathematics are just that, they're distinct. The theory of numbers is one thing and the theory of groups is the other thing. Unfortunately, our thinking about mathematics in that way is not entirely adequate, because even the different vaguely defined layers of mathematics, or let's say the fuzzy nodes that make up the web of mathematical knowledge, are actually interconnected with each other in ways that many of us do not really see or do not understand. And this is precisely what we will see in this episode, because it is entirely possible to take the double counting approach from combinatorial analysis and parallel translate it into the context of finite sums, which again can stand on its own right in the let's say layer called algebra, middle school or high school algebra, or taken further into real or complex analysis with our infinite sum that we will evaluate in this episode. And that ground is quite fertile because let us say we're given a finite sum, and we will write it down as follows. Let's write it down where in the middle over here somewhere. Sn, that is represented as the sum of certain terms, a sub k. Again, let's say k here varies from 0 to n. It doesn't have to, but in general, for demonstration purposes, again, to understand how a certain idea in mathematics works, we will use the material in Einstein's words, as simple as possible, but not simpler. And that sum can be represented as a0 plus a1 plus, and so on, plus an. And quite often, when we are asked to evaluate a certain sum, a finite sum or an infinite sum, what are we looking for? Many people refer to what we're looking for as a closed form expression, and the more you study mathematics, the more you will realize that it is not that simple to define what exactly is a closed form formula. Some students will say, hey Roman, how about a finite combination of elementary functions? We can apply this to, for example, integration as well. We can apply it to summation. Well, at the first level, at first blush, maybe it is okay, but it turns out that if you dig deep enough into mathematics, that becomes not entirely satisfactory. But again, for the purposes of this episode, let us say that given a finite sum, we're looking for an alternative expression E that must be on the, let's say, right-hand side of the equal sign, again, for the purposes of definitiveness. And the moment we see that, what do we have? Again, we have the equality between two units of mathematical information, between two pieces of mathematical information. And again, the ground is fertile for an opportunity to construct, invent, synthesize, discover, pick your favorite verb, two stories. One story that will explain or represent one side of our relation, and another story that will represent the other side of the relation that is captured by the equal sign. And in the context of finite sums, that can be done as follows. Setting up the ground for double counting and setting up the ground for an opportunity to generate two stories, iterate the index or the size of the given sum rightward once by setting n to n plus 1 and writing the given sum n plus 1 is represented as the sum of the terms a k, where k varies from 0 to n plus 1, not n, but n plus 1. And that representation, unzipped into explicit form, looks as a0 plus a1 and so on, plus ak plus an plus an plus 1. Next. For story number 1 in our double counting based evaluation of finite sums, represent the iterated sum as the sum of the first n terms, shown over here, the sum of the first n terms, plus the last one. And what is the sum of the first n terms in our sum is called? The sum of the first n terms in our case is called Sn. So our representation of the given iterated sum Sn plus 1 can be which one? Can be Sn plus an plus 1. And we're done with one story. And now we will construct the story number 2. Represent one and the same iterated sum Sn plus 1 differently as the first term a0 plus the rest ones, like so. And in this case, that representation can be rendered as follows. A0 plus the sum of the terms ak, where k varies from 1 till what is the upper bound of our sum? I'll write it down in red. N plus 1 as follows. A0 plus the sum of the terms of the given sum a sub k, where the summation index k varies from 1 to n plus 1. Next. Precisely because we counted the sum of the terms of one and the same iterated sum, we argue that the results of both of these counting stories must agree. As such, equate the result of the first counting story, S sub n plus a sub n plus 1, to the result of this second counting story, a sub 0 plus the sum of the terms a sub k, where the summation index k varies from 1 to n plus 1, and obtain an expression that reads S sub n plus a sub n plus 1 is equal to a sub 0 plus sum of the terms a sub k, where k varies from 1 to n plus 1. Next. Reindex the right-hand sum that was obtained in the previous step, shown over here, in such a way that the summation index of the new reindexed sum varies not between 1, shown in red over here, and n plus 1, shown in red, but the summation index in that reindexed sum should vary from 0 to n, shown in blue. Blue 0 at the bottom, blue n on top. If you are new to this reindexing business, then in that case, the good news is that there exists a purely mechanical way to do it. For example, I show this way in the upper right corner of your screen. Mechanically rename k into the variable k prime plus 1. Then if we put 1 for k into that equation, we get equal to k plus 1, 1 on one side, on this side, and 1 on this side. Cancel out, and k prime is equal to what? K prime is equal to 0. That's how this blue 0 pops into existence. And when k is equal to the upper bound of the original sum, n plus 1, we write down n plus 1 equals to k prime plus 1. 1 and 1 cancel out again, and we have k prime equal to n, k prime equal to n. And once all the material in the reindex sum is expressed in terms of the variable k prime, again, mechanically chug along through that material and replace K prime back to K. If you do not like K prime, then name this variable J, for example. Do the same manipulations and obtain the result. Once your result is expressed in terms of J's, roll through this material and replace uniformly everywhere you see a J, replace the J with K, and voila, you will have a material. This is important. I represented this material as a function of the term A, K plus 1, because technically that is what you will have, and this is precisely the crux of the problem. All the steps that I outlined so far were pretty algorithmic, and now the non-algorithmic, the art, the mathematical art, begins, because depending on the material that we get precisely over here in this function that is has the A of K plus 1 as an argument, the success or the failure of this double counting way of evaluating finite sum hinges, and the idea here is the following. Precisely because the summation index in the re-indexed sum varies between 0 and n, which are exactly the boundaries in our original finite sum, Sn. Sometimes, and it is important to understand that at this point this is not an algorithm, this is just a heuristic template, another heuristic template that may or may not work, and for the matters of full disclosure, most of the time it will not work. But sometimes it is possible to sculpt the original sum Sn from the material that is baked into this here function, which has the term A sub k plus 1 and the material called x k plus 1 in that sum available to us. In other words, sometimes this here sum that is re-indexed into this shape can be sculpted into a certain function, let's say certain function of precisely our finite sum Sn. And the exact shape of that function, I'm not sure myself how this shape can be algorithmically defined. I do not think so. The only thing that we can say at a more or less theoretical level, that the exact shape of this function, if it even exists, depends heavily on the material baked into this guy right here, into the re-indexed sum. Maybe we can somehow flip this representation into a certain integral, single, double, triple, or whatever. Or maybe there is a derivative of order 1, order 2, order 3 is lurking somewhere in that material. The resultant equation, if we can do that, if we can somehow bake a function that has Sn in it as the main character, could be, for example, that equation could be, the resultant equation could be a integral equation or a differential equation. Again, the fearless prediction here is that most of this time this equation will be so horrible that it will not be solvable analytically and in symbols. This is again for the matters of full disclosure, but there do exist cases when both of these two things are possible. That is, sometimes it is possible to take the material that is baked into the re-indexed sum and sculpt it into an explicit and fairly nice function of our original sum Sn, and put it back into this equation over here and solve that equation symbolically in symbols or analytically, and voila, thus obtain an alternative expression from this equation. Out will pop, remember, our alternative expression for the sum Sn. Again, this may sound too complicated and too horrible, but as is the case with many things in mathematics, theoretical physics, and computer science, any new concept on the first reading sounds horrible and seems to be complicated, but once you step up close and personal and begin studying how it works, the complexity and the scaredness factor dissipates into oblivion. And in order to see how this finite summation based on double counting idea borrowed from or parallel translated from combinatorial analysis into the context of finite sums works, let us apply this double counting idea to the process of evaluation of something that all of our viewers should be comfortable with, or the finite geometric series. As such, given a finite geometric series shown in the middle of the board over here, we want to uncover its alternative expression using precisely the just explained double counting approach for evaluating finite sums. And to that end, we do the following. Iterate the size or the index of the given finite sum rightward once by setting n to n plus 1 and writing down the expression for Sn plus 1 equal to the sum of the terms z raised to the power of k, where k varies between 0 and n plus 1, which is another way to stringize the entire sum as 1 plus z squared and so on, plus z raised to the power k, plus so on, z raised to the power of n, plus the term which is z raised to the power n plus 1. Next. Represent the given iterated sum as the sum of the first n terms plus the last one. That is, write down the expression for the sum Sn plus 1 as Sn plus the last term. What is the last term? The last term is z raised to the power n plus 1 plus z raised to the power n plus 1. But at the same time, the very same iterated sum Sn plus 1 can also be represented as the first term plus the rest. As such, write down the expression for Sn plus 1 as 1 plus the sum of the terms z raised to the power of k, where the summation index k varies from 1, shown in red, to n plus 1, shown in red. Hence, since both of these representations apply to one and the same finite iterated sum Sn plus 1, it follows that these representations must agree. As such, put the equal sign or equate the first representation of our iterated sum Sn plus 1 as the first n terms plus the last one, and this second representation of the finite sum Sn plus 1 as the first term, which is 1, plus the rest. Now that this relation is on the books right here, We carry on the next step. Reindex the right-hand side sum that we obtained in the previous step in such a way that the summation index in the reindex sum runs from 0 to n, shown in blue over here, 0 in blue, n in blue, and not between original 1, shown in red at the bottom, and n plus 1, shown in red on the top, as I explained in the previous segment. And once we do that re-indexing, we will obtain the term that has the following shape: z raised to the power k plus 1. And this is precisely, remember from the previous segment, that's the function phi of a sub k plus 1. This is precisely this guy. And now the fact that the summation index in the re-indexed sum varies between exactly the same boundaries as it does in the original sum presents us with an opportunity to sculpt the original sum Sn from the material that is present in the re-indexed sum. The way we do this sculpting depends heavily on our experience, on our taste, on our depth of knowledge of mathematics overall, and on our overall mathematical maturity. But here, this step is not exactly algorithmic. This is where the art of mathematics is an art of telling a story kicks in. So here, what we do is we look at what we have in the given sum. We look at the material available in the re-index sum, and we try to shape the summoned in the re-indexed sum into the shape that is present in the original sum. In other words, the success and the failure of our endeavor to obtain an alternative expression for a given finite sum hinges on our ability to recognize somehow the original sum in the re-indexed sum, and in some sense more fundamentally depends heavily precisely on the structure of the summoned in the re-indexed sum. In this particular case, we see that the structure of the summoned of the re-indexed sum works in our favor. And how can we see that? Well, the manipulation here is straightforward. We split the power to which our summation variable z is raised as follows. We write it down as this sum that runs between 0 and n. It has the following shape: z times z to the power of k. You see, this is why the structure of the material present in the re-indexed sum in our approach can be split like that, and because that factor does not depend on the summation variable, we can factor it out: z times the same sum over the index k that varies between 0 and n, where z is raised to the power of k. And what do we see? What is this sum? What is this sum right here? Well, if we look at what we have and compare it to what is given, we instantly recognize that what we have now is none other as our finite sum S sub n. As such, we write it down as z times Sn, and this is precisely the thing, if you will, that I referred to in the previous theoretical discussion as the function f of S of n. In this case, we managed to sculpt the given finite sum Sn from the material that popped out of re-indexing maneuver of the sum that came out from this representation of the given sum. And again, this partitioning of the given sum as n plus 1 as the sum of the first n terms plus the last, and as the first term plus the rest, is completely legal, mathematically watertight. Why? Because all the sums are finite. And if the sums were infinite, if we were dealing with infinite series, then with this partitioning we will be asking for trouble. But now that we managed to sculpt the given sum Sn from the material of the reindexed sum, we put that expression back into our workhorse material relation, this one. Where is it? This way. And we bring it home. Now we take our reindexed sum that we managed to express as variable z times the original sum Sn, put it into this part right here. Remember that this part via reindexing came out to be z times Sn, and I rewrote this relation shown over here on top of the board, and now we see that we obtain what? Well, in this case we obtained technically a single variable algebraic equation of order 1 over the set of, let's say, real numbers, or it could be complex numbers, if you will. So such an equation always has a solution, of course, as long as we take z to be distinct from 1. As we know, we will see that in a second, but the point here is that we obtained an equation that can be solved analytically and in symbols, but depending, again, remember, on the structure of what we have in the reindexed sum, maybe here it could be represented, that sum, as the, for example, first derivative, or the second derivative, or the third derivative, or as some wonky integral, or whatever else the case may be. All of that depends heavily, evidently, on the structure of the sums of the given sum. In this case, we obtained a quite manageable equation in Sn that is linear in Sn. And what do we do now? Well, we bring it home by solving it. So what do? We collect all the unknown terms on one side of the equal sign. Let's do it over here. So we will write down Sn minus z times Sn equal to, and we move all the material that is known, let's say, or given to us, to the other side of the equal sign. 1 minus z to the power of n plus 1. Here we factor out one and the same common term, Sn 1 minus z is equal to 1 minus z to the power of n plus 1. All these manipulations are straightforward. You see how that double counting approach applied to evaluation of finite sums, how does it work? And now from this expression over here, we write the alternative expression sought after. So Sn, that is equal to our original sum. Let's write it down. Zk, k from 0 to n, is equal to what? 1 minus z to the power of n plus 1 divided by 1 minus z, provided, of course, that z is not 1, whatever that z is. And in some sense, if we go back again to our theoretical material, that's how all these little theories develop. This is our alternative expression that we originally set out to find. So this is how this approach works. Study it as long as you have to, and if you did not solve that problem correctly on your own, we suggest that, again, you do not watch my next segment where I will unfold the solution of the original problem, but try to apply the double counting approach to the summation of finite sums on your own. To that end, let us evaluate the given sum using the double counting summation idea at a slightly more realistic pace. In our mind's eye, we see right away that the iterated sum Sn plus 1 has an obvious shape, and we represent that iterated sum in two different ways, thus justifying the idea double counting. In the first such way, we represent our iterated sum as what? As the sum of the first n terms plus the last one. What is the shape of the last term over here when the sum is iterated from n to n plus 1? Exactly, that shape will be n plus 1 over e raised to the power of n plus 1. And we also represent the same iterated sum in which shape? The first term. The first term corresponds to the value of the summation index k equal to 0. It is 0, so we write 0 plus the rest of the terms, which are sum of our common term k over e to the power of k, where k varies from 1 to n plus 1. And now we reindex that sum. Remember the next step. We run this sum over the summation variable k that varies between 0 and n. But how does the structure of the summand change in this case? It becomes k plus 1 over e to the power k plus 1. Remember, this is phi of a sub k plus 1 from our theoretical discussion. And now from this material, we want to sculpt our original sum Sn, and this is the step that is not algorithmic. Up to here, the steps were mostly algorithmic. Now, the moment of truth, so to speak, comes about because the very structure of the material that we have in the reindex sum will basically make or break our approach. In this case, how we can represent this sum? Well, we basically divide our numerator by the denominator here, and one copy of e we can factor out right away. 1 over e times the sum where k varies from 0 to n k over e to the power of k. That maneuver is more than straightforward. Plus, again, the same one copy of e can be factored out. And what do we have here? The sum over k varying from 0 to n of what? 1 over e to the power of k. Now we go back and we'll look, what is this guy? Well, it doesn't take much effort to see this is precisely our sum, Sn. And what is this? Well, this is our finite geometric series. We just evaluated its alternative expression using precisely the idea of double counting that we parallel translated from combinatorial analysis. And we keep writing. What do we keep writing? We have 1 over e times Sn plus 1 over e. What do we have for an alternative expression in this case? For the finite geometric series, we have 1 minus e to the power minus n plus 1 over 1 minus e to the power of minus 1, because the common ratio in this case is what? 1 over e. This is the proverbial common ratio r, frequently denoted as r in various textbooks and websites. Now we move e into the denominator here, and what do we have? We erase this guy, we erase this, and we obtain e minus 1. Would you agree? And that whole thing is equal to our original expression, which is what? Sn plus n plus 1 over e to the power of n plus 1, and voila, again, we managed to obtain an equation in Sn that is solvable analytically and in symbols, again, depending on what type of material you would like it to be. This is a single variable algebraic equation of order 1 over the field of, let's say, real numbers, and provided no division by zero happens, this type of an equation always has a solution. The root of this equation is precisely Sn, or whatever material sits on the other side of the equal sign is an alternative expression. So what do we do here? Well, from here it follows that what? We carry Sn to the other side. Let's say, what do we have? 1 over e times Sn minus Sn is equal to our n plus 1 over e to the power of n plus 1 minus, if we take this minus 1 minus e to the power of minus n plus 1 divided by e minus 1. So far so good. Now we factor out Sn over here. This is one and the same summand. So from here it follows what? We have Sn times 1 minus e divided by e is equal to what? N plus 1 over e to the power n plus 1 minus 1 minus e to the power minus n plus 1 divided by e minus 1. So what do we see over here? 1 minus e minus 1. What is the good thing to do? The good thing to do is multiply this whole thing through by -1, just to make it easier for ourselves, make our lives easier. So e minus 1 on this side, e minus 1 on this side, plus sign over here, minus sign over here. We put e into the numerator of this whole mess on the right hand side of the equal sign. We put e minus 1 into the denominator of all these things, and what do we have? From here it follows what? That our finite sum Sn can be evaluated in which way? Work with this guy. One copy of e goes into the numerator, so e minus e to the power e minus n divided by e minus 1 squared minus one copy of e goes here, canceled out with this guy, and we have n plus 1 over e to the power of n divided by e minus 1. This is our alternative expression as a function of n. Some people will say this is our finite combination of elementary functions. And everything is nice and pleasant. This is a constant altogether. This is a constant altogether. So the varying material does not look that horrible. And essentially, the game is over. And why is that? Well, now that we have an expression for our finite sum on the books, all we have to do to solve the given problem is write down the following. Our infinite sum, which was what? N over e to the power of n, where n varied between 0 and positive infinity, is represented which way? By definition. This is not the only way, but the limit when n grows without bound of the above finite sum Sn. So this is the limit of n tending to positive infinity. I'll use square brackets just as a visual candy of what e minus e to the power minus n over e minus 1 squared minus n plus 1 over e to the power of n e minus 1. Again, do not pay any attention. This is not a floor function. This is just a visual candy to separate visually the traditional round parentheses from the square ones. And what do we see right away? Well, right away we see that the exponential function that sits in the denominator here in the second term outpaces in its growth any linear function that sits on the top. And technically, pedantically, we do here, we take our favorite theorem from real analysis, which says what? The limit of a difference is the difference of the limits, provided that the limits exist. And in this case, these limits do. The limit of this, let's write it down like this. This will be a limit of n tending to positive infinity of e minus n over e minus 1 squared minus the limit of n tending to positive infinity of n plus 1 over e to the power of n e minus 1. Again, recursively, we apply a bunch of other basic fundamental real analysis theorems. The limit of a product is the product of the limit, provided that the limits themselves exist. The sum, again, constant, yada yada. The long story short, this limit is 0. It vanishes. Here we split this limit again into two. This divided by this minus this divided by this. Here this guy lives in the denominator. Actually, this limit is 0, so the only thing that survives, let me show it to you guys in red. The only material that survives in this case is this. This is the only material that survives, and this is our answer. So this limit comes out to be equal to e divided by e minus 1 squared, and this is our infinite sum, an alternative expression, which was what sought after. This is the result that was sought after. Again, one more time, you guys already know what I'm about to say. Nobody in the mathematical community cares about this particular result, but everyone in the mathematical community cares about your ability to exhibit a fair amount of intellectual bravery and ask the question that this way or that way not that many students of mathematics ask: what will happen if we step into one vaguely defined layer of mathematics, shuffle it around, pick something interesting that works in that layer well, and then try to steal it in a good way and bring it to another vaguely defined layer of mathematics and see if we can adjust it in some way and make it work over here. So intellectual bravery is one thing, and I will make an episode about being intellectually brave in physics. This is just an example in mathematics. That was one. Number two, you also had to exhibit and show a fair amount of technical prowess, where you took a promising idea from one layer into the other, and you also showed how that idea could work in the new setting and in the new context. And now, also, I recommend that you guys do not just give up, do not throw this idea into a far corner of your mind, but take it further, research on your own situations when the double counting idea applied to the process of evaluation of finite sums does work. Try to find more other types of finite sums where this approach works, and also try to find sums where this approach does not work. Because overall in mathematics, it is just as, if not more important, to see and understand how, why, where things do not work, as it is to see and understand how, why, and where things do work. For example, try to apply this double summation idea to trigonometric sums or to sums that contain factorials, for example. The sky's the limit to your imagination. Report your findings to us. Maybe you can develop this approach into something else where a similar idea, twisted or shaken, somehow can work for other types of sums. Now, this is it for the mathematical problem S3M06, and we will move on to a new challenge next. Our next challenge will be a problem in physics. In season 3, this will be S3P2. This will be the second problem in physics. S3 season 3P physics problem number 2. And the setup in this physics problem is the following. From a known initial height h0 located over here, a material point, a small ball or a spherical chicken of uniform density, is thrown under no angle to the horizon or strictly horizontally with the initial velocity v0 whose magnitude is known. The magnitude of the height h0 is known and the magnitude of the initial velocity v0 is known. It is also known that throwing out the air drag, air resistance, wind, all sorts of realistic conditions and bringing it down to the typical middle school situation under ideal situations in near Earth gravity, uniform gravitational field, the whole thing, the velocity is way smaller than the speed of light, toy conditions. It is also known that once our spherical chicken of uniform density begins bouncing over the absolutely hard or absolutely rigid surface with the condition that all the collisions lead to only the change in the vertical velocity of the spherical chicken in such a way that the ratio of the velocity vertical component of the chicken's velocity after the collision to the vertical velocity of the chicken before is a real number r, which is strictly less than 1 and greater than 0, which is basically to say that every time our spherical chicken of uniform density bounces off of the absolutely rigid horizontal surface, its vertical velocity diminishes by the same amount. This is r right here, real number. The objective of this problem is the following. At some point, our spherical chicken will stop bouncing and it will come to a complete rest. This is captured by this red point over here, and the fact that the velocity v equals 0 precisely means that our spherical chicken of uniform density is not bouncing, is not moving anymore. It came to a complete stop and a complete rest. Bam, with respect to the origin. The question is, what distance, what is the horizontal displacement, or how far horizontally from the point of origin, which is orthogonal projection of the launch point onto the horizontal surface below, did our chicken manage to fly / roll / bounce to? Again, we would like to see all the steps that you take in order to solve this problem. This is it for this episode. Thank you very much for your time. Thank you for watching. I will see you in the next episode, in which I will present my solution of the physics problem S3P2.